How's it going, everyone? Welcome, Eulier Gonzalez here. Now, today let's going to look at the composition, which is part of the functional tools that we're going to add to our tool belt when it comes to write code that is provable, and also when it comes to read code that is provable. That follows this functional approach, aka that at least that any time that we call that function, we know that it won't break the state of the application, or it won't change the state of the app. All right, this is known as referential transparency. So when you call a function and the output of that can be replaced with any, or the output of that function can be replaced at any place on your app, and it doesn't change that. So let me actually go into this. This is the referential transparency, right? So it's a referential transparency when a function that you call, okay, so when you call a function, you can replace the return value, okay, and not affect the rest of the program. So the benefit of the referential transparency is that it's actually from the reader of the code, that you are make sure that anytime that you call that function, the returning value, you can replace that and not affecting the rest of your application. And to do that, we have to look at other stuff to we get here. First things first is to understand what a function is, and also what is the difference between a procedure, that a function it needs to receive an input and return an output. That is not enough, because also you need to follow a certain rules to that. Certain rules to that to prevent any side effects, such as that they must have is a direct relationship between the input of the functions, the input and the output of the function. That those input and the output must be direct, and there must be they must be direct, and there must be also one single input, the same output. So given the same input, the same output. But necessarily they don't need to have is this. So they don't need to be direct inputs and direct output, as long as those input don't change. And we did that with closure. All right. How can we now is wrap a function with another functions and create now a new state of our application that won't modify is the state of that. And also with the same, and also that, well, as I mentioned before, that you must get always the same output given the same input. So this is something that is summarized now, the function purity, all right, known as the referential transparency, this property that a function call must have. So when you now call that function, you now make sure that you can replace the output of, you can replace the returning value in any place of the application, and not modifying the state of the program. So at some point there, of course, are places that you need to actually deal with these side effects, or places that are going to change the state of the application. So we look at a couple techniques when it comes to extract the impurity of their function. One of them is containing the lexical scope when you on your function definition, and the other is now take a snapshot of everything and then restore the state afterwards. Once you run into that function call. So, but in any case, the point of this, all right, is that now by understanding is another concept like argument adapters, in that the functional programmers are obsessed with the shape of the function, pretty much like we did or we are when we now want to go out to some vacations. You are obsessed with all the different boxes and stuff and how you can rearrange them into your luggage. Okay, this is pretty much what they are obsessed with the shape of this function, because this is pretty much like Lego block. All right, so you have now a luggage, and in the luggage you want to have everything there, and if they can be lightweight as possible, that'll be great. But at least you want to all of the clothes, pants, shoes, skirts, underwear, and other stuff, your laptop, now fit together in a way that they are there, right? And that's wonderful. So this is also a good real life analogy of the functional approach, the functional programmer, when it comes to their obsession with the shape of the function. Why is this? Because now you can, is by playing with the arguments of the function, which is the value that we pass to a function, unlike a parameter that is from the function definition, is the name of the input of the function definition. So by playing with the argument, which is the number, the shape, and the order of stuff that we pass to this function, or the number and shape and the order of this that we or that come out of this, okay? This is now when we slowly but progressively start to play with our function, adding the functionality that we need to, and therefore look at some other concepts like point free. Point free, which is the way of how you can now define the function relationship without specifying their data points, which is a great stuff, all right? Even though the 99% of the programmers agree to be, so being more declarative is way much more interesting, or is way much more meaningful than being implicit. But in this case with point free, we can now describe the relationship of the function by using now is a concept known as generalizations and specializations. So anytime that you're going to run a function, okay, it is important to know when you want that computation to happen, whether it's eagerly or lazily, right? So despite where you want to do that, because there's some scenarios that you need to run that when you need to, or you can run that initially, right? There are now a technique called memoization that allow us, when it comes to run some functions, to decide if we want to catch that computation. So subsequent values would not be recomputed. You just only have access to that. There's also a trade-off with this, because now you are increasing the memory size, but like anything in computer programming is like that. So you have now the constraint of time, space, and readability. So once we know what these memorization techniques are, it looks like, can you also from this Randa library that you can use as a way to say, hey, I want you to now is closing over this variable that I want to now memorize, whether it's you're storing is some hash map in there or some sets, whatever. That's something powerful, some data structure here. So why we are bringing that here? Because once we know about this memorization and the idea of the functional programming of generalization and specializations, that when you combine that with point three functions, to now have confidence that that function will execute anytime that that function run, the returning output, you can replace the returning output without modifying the state of the application. So you can replace the returning value of that and not affect the rest of the program. So this quick overview of generalized and specialized is because you can now define is general utility functions like this, and then if you need to get a specific functionality, you can now apply some of the arguments right now and then later on call as partial application, or you can now wrap that function that accept one input at a time, known as querying. Why this is important? Because at some point you want to apply this particularly techniques, specialization techniques, when it comes to, let's say you want to provide a preset of functionality initially, all right? Let's say some configuration variables initially, and by the time that that runs, then you want to apply the rest of the arguments. You want to pass now the relevant data as it is. So this might be a good example of partial application where you want to you want to preset some configurations. And for querying, which is the preferred method of passing inputs to a function one at a time, effectively creating now a closure, because now querying is just a way of how you can pass or how you can transform the function input into a series of functions that takes one input at a time, all right? And most of the time you're gonna see stuff like loosely querying, which is where instead of passing all of the input one by one, you can pass two or more inputs per function call. That is the key of this, of the partial application and querying. So actually it's not that hard, by the way, it's not that hard. We also need to remember that it is important for the function programmers that the number, the shape, and the order of arguments that we pass is important. So that's what we pass now initially is the more general arguments, and then the more specific one. So for example, like this, that's what we pass now is a function to the map function, all right? And because now the map function required is to pass is one single value to this, and then now apply that to all of these elements on the collections, we are now effectively are changing the shape of the function here and then returning that with a different shape, right? So we are fixing here is that functionality here. We're essentially here doing a partial application. So we're doing this partial application and then apply that to. And why this is important? Well, because now we can have this specialization adapt shape. So we can rewrite this in terms like this, all right? And to say now, hey, we have now a query function that is going to transform all of those inputs into one single values. So therefore, we can say, hey, I want to now add this as expected. This is quite interesting, right? This is quite interesting. So you can define is add query the add, okay? in terms of this function, this point free definition here, that you're gonna get at, that you are now can pass is one value at a time, right? So behind the scenes, this query function is just transforming that function in transforming the functions. Instead of receiving is all of the argument at once, it's going to receive all of the arguments at function call. All right. So this is an extremely common technique in functional programming. So let's go into now. Okay, let's go now to move through the composition, and here we are.
All right, let's talk about composition. We briefly mentioned this one earlier as well when we were talking about point free. Let's dig into composition. Let's understand the idea of one function's output becoming the input.
Let's say composition. All right. Which is the idea of one function's input, one function. So is the idea of one function input is the one function's input is the output, is the function output of another. What is the idea of one function's output? One function's output becomes the function input of another. Okay, that's the idea. It's the idea of one function's output becomes the function input of another. That's the key idea. That's the key idea of it. That's the key idea of composition. So the function output, one function output is the function input of another.
Input to another function. Here's an example. I've got three unary functions, a -2, a triple, and an increment. And they do exactly what you would expect. -2 subtracts 2, triple triples it, increments by 1. On line 6, I'm going to call increment with 4, because that's my base shipping rate that I'm going to start with, or that's one of my base inputs for calculating a shipping rate. And then that gives me a temporary variable, and then I'm going to pass that value, line 7, into the triple function. So I went from 4 to 5, and then I passed 5 into triple, which triples it. That becomes 15, and I save that into temp. And finally, I pass that 15 value into the -2 function, line 8, and that gives me the end result, which would have been my shipping rate being added to the total cost of this problem. Okay? This is a scenario that we're going to use over the next several slides to try to illustrate the idea of composition. And what you need to get out of this, the takeaway that you should be looking for, is becoming familiar enough with this pattern that you spot when one function call is producing an output that is then later routed to another function call.
So this is the pattern that we need to focus on when a function output, when a function called becoming
pattern that you spot when one function call is producing an output.
Exactly. When a function call is producing an output that is redirect to another function input
that is then later routed to another function call.
Or that is later later redirect to another function call. So anytime that you've called a function, the output of that is redirected at some point later. For example, like this, is redirected at some point later. Uh, it that will redirect into another. Yeah, it will redirect. Is exact. That is later redirected to another function call.
It is often the case that it'll end up in some kind of variable, and then that variable gets passed. Sometimes you'll see it literally written with them nested, like one call inside of another. But more often, you'll see them assigned to variables, sometimes like temporary variables like you see here. And you want to get to the point where you can recognize, aha, that's a composition. Okay, that's the takeaway. That's the
So you want to reach a point when you say, aha, that's a composition.
The final summary. Okay. So what I'm going to do to illustrate composition for you is I'm going to ask you to switch your brain between the code scenario that we're looking at here, and I'm going to ask you to look at a metaphor that I'm going to use to describe it. Okay. As we talk about this metaphor, the first step that I want to address is this idea of abstraction. How many of you have heard that term before, abstraction? Okay. Abstraction is one of those terms that is thrown around in programming.
Okay. So here we are going to look. Okay. So here we're going to look at the idea of abstraction first in the context of function.
And nobody really can like pinpoint and say definitely this is what I mean by abstraction. It seems to have lots of different meanings in lots of different places. But I want to talk about the original idea behind abstraction. The original idea behind abstraction is that you have two or more things in, say, a piece of code that are intertwined together. We could look at lines 6, 7, and 8, and we could say that there are two distinct concepts happening here, and they're interwoven. One of the concepts is that we're calculating a shipping rate, and one of the concepts is that we're adding that shipping rate to the base total for this order. Those are two distinct concerns, but in this particular piece of code, they're wrapped up together. Okay? The initial, original idea of abstraction was to tease apart two things which were otherwise intertwined together. To tease those two things apart so that they are separate, and by way of separation, we insert in between them a semantic boundary that allows us not to hide one or the other. That's what a lot of people think abstraction is about, hiding. It's not about hiding. It's about separating. Abstraction is saying, take these two things, separate them, so that I can look at this thing and understand it, or look at this thing and understand it, without, while looking at this thing, having to worry about this one, or vice versa.
Okay. So abstraction is a way to tease things apart that when I look at one, I can understand it, and when I need to look at the another, I can understand it as well, okay, without needing to depend on another, without the need to depend on each other.
By separating them, we make them easier to understand, easier to analyze. So,
So by separating them, we can make them easy to understand and read and analyze it.
how would we abstract lines 6, 7, and 8? not hide things, but rather separate things. That's what I want you to keep in the back of your mind as we go throughout this discussion. Okay? So the metaphor I'm going to use, and we're going to be mentally jumping back and forth. So hopefully you've had your caffeine. Hopefully you're ready to mentally jump back and forth between these two scenarios. For this scenario, I'm going to ask you to play as if you are an engineer at a candy factory. Okay? And at the candy factory, you have these machine setups like you see here. You got these machines with conveyor belts in between them where they produce the candy step by step by step down the assembly line. Okay? So on the far right here, we see a machine that, you see my great art skills. I'm a pretty good artist here. You see this machine that takes melted chocolate, you pour in the melted chocolate, and what comes out on the bottom is these cooled blocks of chocolate. Okay? That's what machine 1 does. Those cooled blocks of chocolate rumble down the conveyor belt to the left. They go into the next machine whose job is to chop it up into tiny little pieces. And so those tiny little pieces are coming out of that machine. They rumble down another conveyor belt, and they fall into the third machine, whose job is to wrap them up in the nice candy wrappers, and those roll along to the next machine, which packages and so on. Okay? So in this candy factory, we've got a couple of these contraptions, if you will, these machines set up on the factory floor, and everything's going well. You're the engineer who's responsible for managing all these machines. One day, the CEO, the owner of this, president or whatever, of this candy factory, comes to you and says, hey, you've been doing a really great job, but we've got a little bit of a problem, and I want to see if you can think about how we could fix this problem. Okay? Because he says, the problem that we have is that our competitors are producing a lot more chocolate more quickly than we are. Like they're producing 3 or 4 times as much chocolate every day as we are, and we're losing to them, and we got to figure out a way to catch up. We need some way to catch up. So the boss is basically saying, can you figure out some way for us to make more chocolates? Now, you know that these machines can't be sped up. We can't, make them run faster. So the only way to make more chocolates is to have more machines. We're going to have more of these set up. And the problem is we don't have room on the factory floor. They're taking up so much space. We only have room for a couple of these in the factory. So you begin to roll around in the back of your head thinking, how could I make more room on the factory floor for more of these machines so that I can make more candy? And we could keep up with our competitors. That's what you're going to be thinking as an engineer at this candy factory. Now I want to press pause on that scenario. And I want us to go back to that code snippet that we were just looking at. Remember the code snippet where I had those temp variables? Okay? Those temp variables are kind of cluttering things up, and they're not really benefiting us anywhere very much. And so we think, you know what, let's just get rid of the temp variables, and let's just have each function call nested inside of another function call. Call increment 4, and then pass that to triple, and pass that to -2. And then bam, we've calculated the ship.
So back to our example. So we can say something like this. So we have if one variable, okay? So we have one variable that says like, hey, let's going to now call it this, and this one, and this one.
Anybody ever done this before? Have you ever nested function calls like that before? Okay. So whether you knew it or not, you were doing composition. That's a function composition, taking the output of one function, making it the
But
input
again,
of another
it
function.
needs to...
We got rid of those messy, ugly temp variables that were taking up too much space in our program. You with me?
Got
We've cleaned up the
rid
code.
of the...
Let's go back to the candy.
So we can just add some so we can just add more machines to our factories because we don't have it, right? So back to our example here. So we get rid of the additional unnecessary space like this. So we get rid of the additional unnecessary space and do a composition. However, if we go back to our candy factory Example. Here the relationship is not
Okay.
clear.
You're the engineer and you've been thinking to yourself, you know, I think what we ought to do, I think the big problem is that those conveyor belts are taking up too much space. So you get this brilliant idea one day. You say, what if I just took out all the conveyor belts, and what if I just stacked the machines right on top of each other? And I've got one machine at the very top where we pour in the chocolate falls out of that machine directly into the next one, it falls out of that machine directly into the next one, and so on, and bam, problem solved, because now I can install many, many more of these on the factory floor, because I got rid of all that unnecessary clutter of all those conveyor belts, all those temporary variables. You with me? So you install the solution in the candy factory, and all of a sudden the factory starts producing more candy, and everybody seems happy, and the boss slaps you on the back and says, great job.
Factory, so I rearrange it.
Things go well for 6 months.
Produce.
And then one day the boss comes to you and says, hey, we've got another problem. I need to see if you can try to solve
like
this. We like the fact that we were able to produce more candy, but one of the problems with this new solution that you came up with, our factory, the line workers, they've been complaining because these machines being stacked on top of each other, it's very cluttered. Like there's wires all over the place, and they have to remember to push the button at exactly the right time, and there's too many buttons to push and too many wires. Is there some way that you could just make a single machine that they pour in the chocolate and out comes the wrapped candy? That's what the boss says, right? You know, because bosses, they don't think in terms of reality. They just say, you know, you engineer, go make it happen, okay? So you're basically asking you to invent some kind of machine that does it all in one. Takes the cool chocolate, the melted chocolate at the top and spits out wrapped candies. Make it easier for all the factory workers. And you're thinking to yourself, well, even if I could do that, it would be difficult for me to maintain each of those individual steps and pieces. I'm going to have some way to access what's going on, right? So this is what's rolling around in the back of your head. You're the engineer, you're trying to figure this stuff out. We have the same problem back in our code base, which is that we've got the place where we're calculating our shipping, and then we've got the place where we're adding that to the total. And these two things are all wired up.
So we have
it's hard to reason about each one independently. So you think to yourself, I know I'm a good engineer. I know what I need to do. What I need to do, write a function.
We have the same problem in
Make a function called shipping rate, which does that work. It does -2, triple, and increment. It takes in the value. And now look at line 12. Line 12 is much cleaner because line 12 is semantically separated the two concerns. Line 6 is where we calculate where we say how to do the shipping rate calculation. And line 12 is where we say what to do with it, which is to add it into the order total. This is called an abstraction. And the semantic boundary that we inserted is the function name. The function name shipping rate is the semantic boundary between how to compute the shipping rate and what to do with the shipping rate.
Because
those are the two separate concerns that previously were all intertwined together. How to compute inserted, added into the order total. This is called an abstraction. And the semantic boundary that we inserted is the function name.
This is called an abstraction. And the semantic boundary that we added is the name of it. So we can look at one thing. So we can look at these things right now. It's like, so we can look at these things right now. Okay. So we can look at these things right now. So we can look at one thing, at shipping rate, and understand it as well as -2, triple, and increment.
The function named shipping rate is the semantic boundary between how to compute the shipping rate.
The name shipping rate is the semantic use of how to compute the shipping rate.
And what to do with the shipping rate. Those are the two separate concerns that previously were all intertwined together, but because we made a function,
And what
now they're nicely
to
cemented.
do
So back to the
with
candy
the
factory. You've been thinking about this for a while, and you think you've come up with a
shipping
brilliant solution.
rate?
I don't need to change anything about the machines. All I need to do is wrap one nice little clean box around the whole setup. Just make one nice big box that's wrapped all the way around all those internal machines. And on the inside, there'll be a nice access panel where I can open it up and get it all this big box solution. So back to the candy factory. You've been thinking about this for a while, and you think you've come up with a brilliant solution. I don't need to change anything about the machines. All I need to do is wrap one nice little clean box around the whole setup. Just make one nice big box that's wrapped all the way around all those internal machines. And on the inside, there'll be a nice access panel where I can open it up and get it all the machines and wires and buttons if I, the engineer, need to work with it. But the factory workers just have one on-off switch. They have one input valve at the top where they pour stuff in, and out from the bottom comes the candy, wrapped and nice, ready to go. And you're thinking to yourself, this is the best of both worlds, because the factory workers only care about input and output. But I, the engineer, I care about how it gets done.
Mm-hmm. So back to our example, back to our factory example. Okay, back to our factory example. As the factory worker only cares about the panel, we as engineers care about how the thing works.
What have I done? I've created an abstraction
Here.
for my composition. All right? I've wrapped it in a function. That's what this big box is conceptually. You implement this solution.
So I create an abstraction.
And then you get some feedback from the boss. He says, oh, the factory workers love it. They think it's great. Every day they're coming in, they're telling us how easy it is to push the buttons, and our other maintenance engineers can open up the access panel whenever they need, and it's all nice and great job, great solution. 6 months go by, everything's been humming along nicely, and the boss comes up to you one day and says, I got another problem I need you to solve. This is a very needy boss, right? Got a lot of problems for you to solve. That's good job security, man. All right, so this has got another job for you to solve.
That's good.
Another problem.
That's good for job security.
You see, what we've noticed is that our competitors are able to come up with new kinds of candy almost on a daily basis. They try out one kind of candy one day, and the next day they're producing an entirely different kind of candy. It's amazing how quickly they can just spin out new kinds of candy, and we're not able to keep up with all the different kind of experimentation that they're doing. We just only produce the one kind of candy over and over again. And we've tried, we've experimented, but it's too slow to make these single boxes with all these machines configured. Can you come up with some way for us to do this more efficiently? For us to make these machines that make our candy for us, but we want to make them more efficiently. Without even realizing it, the boss is asking you the most ludicrous thing of all. He's saying, could you make me a machine that makes machines?
So the boss, so the CEO is happy with the solution, happy with the solution. Factory workers love it. Factory workers love it. And the engineering team can come and fix or add new stuff into this new machine. 6 months pass, and the CEO now needs a new problem to solve. Can we make a machine that produce other type of candies. Okay. Can we make a machine that produces other types of candies? Interesting. In other words, the CEO is asking a ludicrous, a ludicrous asking, in other words, the CEO is asking a ludicrous thing. Can you make machines that makes machines?
A machine that takes machines as inputs and outputs other machines. Could you make me something like that? Go invent it. This is a real head scratcher. It's going to take a while to try to invent, okay? But you'll work on it. Let's switch back to the code. We've been thinking about that shipping rate calculation, and it's been going along fine. And then somebody else in the company says, we actually have different kinds of shipping rates. We have like international shipping rate, we have domestic shipping rate, we have like express shipping rate and overnight shipping rate. We need to, but everywhere we keep defining all these different functions is cluttering up our code. Could you make it easier for us to define these shipping rate functions? So you, the programmer, think, well, sure. Because there's a pattern involved in defining each of these functions, which is that each of the shipping rate functions takes a different set of 3 functions and calls them in succession. So you think to yourself, I'll just make myself a utility. And maybe I'll call this compose3. It takes 3 functions, fn3, fn2, and fn1. I'll explain why that ordering in just a moment. It takes those 3 functions, and it produces a new function, which will call each one of those in succession. First one gets the input value. Output of that becomes the input to the next. Output of that becomes the input to the next. And the output of that is finally returned. And you notice now that you can just define as many shipping rate functions as you want. You make the original shipping rate function like this, but later you might say the international shipping rate, and instead of saying -2, you say -1, and instead of saying triple, you say quadruple, and you just pass in different functions, and you get a different shipping rate function as a result. Can you see why the definition of shipping rate on line 5, not only is it point free, but it's more declarative? It says to somebody who knows what composition is, I know that it's going to go in order, I know that it's going to go in order from right to left. It's first going to call passing any input to increment, then it's going to pass the input to triple, then it's going to pass the input to -2, and finally it's going to return the result. Right, functional programmers know that a composition works exactly like that. If you have a list of functions, it will execute them in right to left order, passing the output of each one as the input of the next, and finally...
Exactly. So back to our code example. Exactly. No. Compose 3. So you say finder here, compose 3. Then you know define is this particular function here to actually know this. So composition in functional programming is to say, hey, so composition in functional programming is to say, is to pass a function that will, is to pass a function from right to left, okay, from right to left, where the output of increment will be the input of triple, in their output, and that output will be the input to -2, right?
Of that is finally returned. The international shipping rate function as a result.
So you can
you see why
compose
the definition of
several
shipping rate on line 5,
shipping
not
rates.
only is it point free, but it's more declarative. It says to somebody who knows what composition is, I know that it's going to go in order. Oops. I know that it's going to go in order from right to left. It's first going to pass in any input to increment. Then it's going to pass the input to triple. Then it's going to pass the input to -2. And finally, it's going to return the result. Functional programmers know that a composition works exactly like that. If you have a list of functions, it will execute them in right to left order, passing the output of each one as the input of the next, and finally giving you that result. And what we see here now is that composition is declarative data flow. It is the flow of data through a series of operations defined declaratively rather than imperatively. Here's why this is so critical. Your programs don't mean anything if they don't mean data flow. The whole point of your program is to have data coming in, doing stuff, and then going back out. So your entire program is a series of data flows. It's a series of state transition management.
So your entire program is a series of data flows. A series of transformation from one input, pass that out, transform, apply this transformation, and then returns it.
Data flows. And the functional programmer knows if that's what our programs are about, then I should declare my data flows in a clear and obvious way, rather than having my data flows implicitly linked. This function calls this one, who calls this one, who calls this one. Anybody got an application like that where functions call each other all over the place? Tracking the data flow is pretty difficult, isn't it?
Yeah. So tracking the data is pretty difficult. That's why I prefer this TypeScript.
How easy is it to track the data flow on line 6? It's as easy as going from right to left, isn't it?
Yeah, by going into shipping rates and then call the shipping rates to say, hey, this will be pass 4, and then pass will be the input of the increment with add 1, and then now that will be the output will be 5, the input of triple, that I'm assuming that is triple, okay, that which is 15, and then that output will be now the another function called -2, which is now 13, and that'll be the shipping rate. So the data flow here is way much more declarative, bro. Oh crap.
Composition is so critical to functional programming because the entire point of your program is to have data flow.
So composition is critical to functional programmers because the entire reason of a program is to have data flow, and it's also increase the readability of the data flow.
That compose 3 utility, by the way, that I invented for the purposes of this discussion, there's a general form of that which we'll get to later, and it's just called compose, and it takes any number of functions. So you could compose 1 or 2 or 5 or 100. It's a general compose utility, and it's provided by all your favorite functional programming libraries.
It makes a lot of sense with this.
One final time, let's go back to that candy factory. Because you, the engineer, have really been working hard on this, and you have a big unveil to the boss, and you say, I have finally cracked the problem. I realize that all the machines that we use to make candy all have a standard input and output valve. And they all have standard ways that the wires plug and the on-off switches work. There's a nice standardization here. So what I realized is I could make a machine-making machine. Drop in any 3 of those machines in whatever order you want, and out spits the nice boxed machine with the on-off switch exactly the way we want. Now, I know it's stretching the metaphor, but hopefully you're seeing the connection to what we did with the compose 3 utility. The compose 3 utility is our higher order utility, our higher order function, which is a machine-making machine. It takes machines, aka functions, as inputs, produces another function, another machine as an output. That's what composition is all about.
A machine making another machine.
So we can take that same compose3 utility and
Because
use
it's
it multiple
producing
times. If I call it with -2, triple, and increment, that's the F composition, then it's going to first increment and then triple and then -2. But if I give it those in a reverse order, we end up with a different kind of function which produces a different result. The same input 4 to F produces output 13, but the 4 input to P produces 7. Why? Because the number 4 is incremented to 5, tripled to 15, and -2 to 13, versus 4 minus 2 is 2, tripled to 6, incremented to 7. So that math is not commutative, and that's why we end up with a different result. Two different, as we said, shipping rate functions. Okay? But what if I wanted to define them in the opposite order? You could envision, if we've envisioned a compose 3, you could envision a pipe 3, which we list them in the opposite order. Look at line 11 compared to line 5. Line 11 has them listed in the same order as line 5, but it produces the result that is the same as line 6. It's the same as the P function. So in other words, pipe goes left to right, where compose goes right to left.
Could you explain why? If it's beyond the scope of this, that's fine. But if you could just quick, like, why does that go off the back end and the pipe go?
So why does compose go right to left, and why does pipe go?
Exactly. So because here it will say, hey, the increment here of pipe by saying is like -2, which is 2, and then there will be the input to this and say 2 times 3 is 6 plus increment, which is 1.
Left to right. Okay? I don't know the canonical, like, absolute correct answer to that, but I can give you some anecdotal evidence for this. If you think about something, imagine a function call where you say a parenthesis, I'll do it backwards here, a parenthesis, b parenthesis, c parenthesis 2. So you're listing them in A, B, C order, right? What order are they going to execute in?
They should just go A, B, C. No.
When you have A parenthesis and then B parenthesis and then C parenthesis, C executes first and its output goes to B. Remember back a couple of slides, that compose utility? There's my FN2, FN3, FN2, FN1. Which one executes first?
The
Well,
F1.
compose, so it's the F1.
Well, don't worry about what compose is. Just look at line 3. Those three functions.
Oh, okay. Because the F3 function is executed first.
Function calls, which one runs first?
Are we going?
So Fn3, because JavaScript say, hey, I'm gonna run this function F3, that now I'm receiving is as an input the F2. All right, I'm receiving data functions that I'm going to call that function. Okay. So this function, what is the end goal of this? Is to see that at the end of the day, you are now adding these functions to the call stack. In this case, in this order. And this is the way of how now it's calling. It's not calling from this. It's not calling this function. Is evaluating this first function.
Going off of the Dear Ask My Aunt Sally stuff. So it'd be F1 because that's inside the inner parentheses first.
That one has to execute first to produce a value that then gets passed to Fn2, which then produces a value that goes to Fn3.
So is it kind of, it's similar to the orders of operations in simple algebra that you would do the whatever's in the parentheses first and
the simple way of saying it, that's the way our JavaScript syntax works, right? The way function calls work is that arguments are passed in a parentheses set, and the argument has to be computed before the function can be called.
And the argument has need to be computed before the function. Okay, and the argument has to be computed, bro. Okay, that's a very interesting here. So from this example here, so the argument needs to be computed. So from the following example, the order of which this function is executed is just like algebra, okay? Or in other words, so the argument the argument needs to be computed first before we call the function. And that makes a lot of sense. So even though that you call fn3 as a function call, but this doesn't have now is the argument computed. So now we call is the function in2 here, and the function in2 and the function in1 is now computed now that you receive the argument.
If the argument is itself a function, that function's got to be called with its arguments. If that argument is a function, call that. So just by virtue of the way the syntax works, you have to go sort of inner to outer. It's not really right to left, it's inner to outer. But in this case, it happens to execute in a right to left fashion. So if you think about compose, if I had a code literally that looked like line 3 somewhere in my app that said fn3, parenthesis fn2, parenthesis fn1, parenthesis some value. If that code existed in my app and I wanted to refactor that code to use a composition, I would write compose, and what order would I list the functions in the compose call? fn3, fn2, fn1. In other words, I would write the compose call in the same order as what is the equivalent of calls, and that's why it has to execute right to left to preserve the same semantic. That's anecdotal explanation. I don't know if that's really why they define it that way, but in my mind they define it that way because it matches the source order. Okay? Let me jump back here. Pipe is an important operation because it has the left to right ordering, and sometimes our brain is actually thinking, which one am I going to do first? That's the thing on the left. I'm going to do -2, and then I'm going to do triple, and then I'm going to do increment, line 11. So sometimes it's more convenient for us to think left to right. Oftentimes it's more convenient for us to go right to left. Similar to what I said before, where more people tend to, in my experience, more people tend to start off preferring partial application, and then eventually they become converts to the school of currying. The same thing seems to be true with piping and composing. People that are not that familiar with all of the ins and outs of functional programming, maybe they dabble in it, but they don't do a lot of functional programming, they tend to like piping
Exactly.
more, because they tend to think left to right, and right to left seems to be confusing and weird.
In my case.
The more you do functional programming, the more you will realize you're going to use compose far more often than you use pipe. So it's one of those things that is counterintuitive at first and then becomes more intuitive as you get more experience with it.
Absolutely.
All right, well, it's time that we practice this composition. So we've got a quick little exercise for you. We're going to define our own general compose and general pipe function. Rather than having one that can only take 2 or 3 or 4, we want...
All right.
want to write general functions that can take any number, 2, 3, 4, 100, however many that we pass. All right, well, it's time that we practice this candy factory, composition. So we've got a quick little exercise for you. We're going to define our own general compose and general pipe function. Rather than having one that can only take 2 or 3 or 4, we want to write general functions that can take any number, 2, 3, 4, 100, however many that we pass. You'll notice in the setup for this exercise, we have several functions provided, increment, decrement, double, and half. And then here are your compose and pipe functions that you want to implement. And you'll notice that you have several functions set up here at the bottom. That's the ones that you're going to test with. And so you want to make sure that at the end, all of these print true. You'll notice that in each case, the compose and the pipe are deliberately set up to be the reverse of each other. So that's why F1 of 3 should return the same thing as F2 of 3, because compose with increment, decrement should be the same.
Should be the same as pipe and
Same
decrement.
as pipe with decrement, increment. Okay. One last little hint in implementing compose and pipe is that you really only need to implement one of these two. Pick either compose or pipe and implement it, and then the other one can be implemented in terms of the previous one, but just reversing the list of functions that you pass in.
Let's get into this, my fellas. Let's get into this. All right. Yep. Absolutely. Let's get into this. Performance, no. Some hard parts, no. See the system design, and see the functional light. Right, so let's get into this. Oh, now we are expanding our mindset. Oh, I love it. Here we are. Okay, good. So we have git log, close purity. Let me actually use git log graph and decorate. We make a merge. You know, this is what happens when you do this kind of stuff, merge and that kind of stuff. Head, which is now whatever branch you are currently at, that's where head is pointing to, which is closure. Okay, and then we have now pointed to closures. But here we already wrapped this closure. So we are now look at this. We have main, we have point free, we have impurity. You know, I really love about this. Oh my God, yeah I do. So if I say branch, for example, I want to take a look at all of the branch. You can see closure, impurity, main, point free, and all of this remote branch, right? Git status, I don't think we have any change. We have change. I want to see is a git diff of these changes here. Most likely is you know what? It is time to look at the previous changing of branch. Let's get into this. A graph, decorate one line. All right, awesome. This is the close purity, the closure exercise. That's right. Also, AutoGen has now these changes. And if I want to inspect what is the changes that this has, you can say, hey, get cat file here, not with this, but with this, and then go walk through that directory that contains now is the first. So git cat file here that contains now is the diff of the readme, closure, impurity, point free, and scopes. All right. In my case, I want to inspect is the cat file of the closure 3.7 of the closure, and this closure. Alright, have now these changes here. As you can see, this actually contains the entire state of your repo and those changes that you applied to, right? So the change that is now looking at this is the x.js, which is the x.js. If we take a look at the cat.file minus b, the x.file is 367. So we want to take a look at the content is this one, right? So here, this is the actual content of the entire file that now Git is being tracked or has track of. I tell them to track of. Interesting. Oh my god. Oh crap. Oh jeez. And our change say, hey, our diff. So get diff of closure is that. So that we change is just what we want to return. So in my case, it remains the same change. We just only add some more padding or not. So that doesn't change that much. But when you run now closure here, in other words, you say nano dot closure dot x dot gs. Okay, then we see here we just only add is less padding that it is. So here we are effectively now creating is a closure, okay, but instead of modifying is the state here, where any time that we are returning that, we are giving is this new state, or we are calling is the function with the new state and the new state and so on and so forth. That's pretty interesting, this particular pattern here. I don't want to save this. In fact, I don't want to actually do something here. Say status, I want to remove this, say restore the file here, closure x. So now our git is clean. You say git add git add like that, git log in one line. That's what it is. Git status. We don't have anything, and now I want to create is a branch, or I want to branching off from the closure, or I prefer to say, hey, I want to branch off from main by saying, hey, git checkout minus b, but I want to do that from main. So I can say git switch to main. All right, and then I say git now git. Let me actually do something here, because I wanna see if I merge those changes in the repo GitHub. Yeah, I want to check that out here. If I merge that out here. The section API with template. Oh, but this is more like exactly function light here. As you can see here, this is a P error from closure. Let me actually close this. We're gonna merge this. There you got it. Now it is merged. Okay, that is good. So now we fetch is the latest change from this. Say pull origin. So you can say pull to actually fetch the entirety of the history of Git. Because this is a small history, it will be quite fast, as you can see, right? It do a fast forward because we didn't have any because our Git history doesn't have any different history. We keep the same history, which is great. And here we can say, hey, now that we have on the main locally is the merge from closures, the merge from point free, and from impurity, right? These two branch here. So far so good. It's like good, awesome. It's going to create now a new branch from main. We're gonna call it is composition. We create now this, okay, and let's go now to here at the exercise file. It's gonna do, I don't need to download that. I can say it's Finder and desktop touch front end blah blah blah. Now activities download. I think this is on the last one. Light. So download light. Functional light. You got it. And composition. That's right. Good. Awesome. Let me actually can I get the Can I actually get this one? Let me open up here code here. There you got it. And I want to add now a new file folder hole. Say make dir composition. You got it. And let me actually drag and drop this. Do that on the composition, and let's go to the code. There you got it. All right. Awesome. Good. On the exercise, I'm going to create now this stuff here. Yep. This is my guess. And here we are. Just going to change that out here a little bit. Functional like okay, I get it. Let me actually change that to code. All right. Show you this. So here, let's go to read the README file here. Say README file, close, impurity scope, closure, point free, composition. Here is this one. So define a compose that takes any number of functions as individual arguments and compose them right to left, right? The other is define a pipe that takes a number of functions as individual arguments and compose them as left to right. This is, you can define this in terms of one or another. So here we're gonna do is something like this and say, hey, because we want is to now define a compose by returning is a high order function, a utility function that say, hey, I want you to now take the arguments of this function, okay, which is the function. Okay, that's gonna call this, right? So by the time you call compose, I want to now is receive this set of arguments, right? So I want to receive this set of arguments. So here we can say, hey, these arguments that will be our functions as an array. I want to call them is in that particular order, from right to left. So how can we do that? Since here we have now is these collections of arguments, by running them, and say I want to, let's say, call, okay, or I can do something like this, but remember that this is now a collection. We can do something like map, okay, and whatever function that you receive here, I want you to now is call that function okay. I want you to call that function, and here is the fun part here. What are you gonna call this function? What are the arguments that this function is gonna be called? Right? So that's what we need to define this as another function. We're gonna call, here's the, let's say, arguments. No? Say is another function here. We're gonna receive is the arguments, right? And here we can say is, hey, by the time that you call this function that we're gonna receive is the arguments, okay, as a collection of values, whatever it is, okay, then I want to now the arguments that you receive here, call that function, and that return output will be now the input of the next one. Because now what it's doing is just applying is, so taking this function here, you say, hey, the first time, now that I received this list of functions, okay, I'm going to go over the first element on this function, okay, and I'm going to now apply those arguments, and I'm going to pass the arguments, run this function, and I'm going to do that for the next one, and I'm going to do that for the next one. So the returning value here will be now the input of another file. Okay. So this is our collections of functions, all right? The first time we're going to call this function and we're going to pass these arguments. So the return value, all right, I want you to be is the input of the another value. So this is where you can apply something called like reduce, okay? So something like reduce here. And why reduce? Because reduce says like, I'm gonna take the accumulator and the current value, which is the function, and I want to say, hey, whatever I have in the accumulator initially, that'll be is the arguments that you pass here. Okay, so whatever I have on the accumulator, so the first time that I pass here, that'll be is the accumulator. I want to now is call that function with the accumulator. I'm not sure if this is actually going to work because I don't foresee this kind of stuff of the compose and all of that. Because what we're doing is that, hey, this value that I'm receiving here, okay, this value that I'm receiving here, that is one single argument, all right, for the sake of this example, that'll be is the accumulator. I want you to now is call that with the function at that moment, that the returning value of this reduce will be now our accumulator, and then you're going to run to the next function call, and the input will be this new one function, and so on and so forth. That is quite mind-bending if this is actually work.
We're just reversing the list of functions that we pass. Okay, let's talk about the exercise on composition. We could either implement compose and then pipe in terms of compose, or reverse. I'm actually going to do the reverse, and the reason is purely for simplicity. Because pipe goes left to right, I can use a very convenient for loop. But there are lots of ways to implement either compose or pipe. Use right or utilities like that. I'm just going to use a simple for loop. So, pipe is going to take in a list of functions.
Mm-hmm.
Gather those up into an array called fn.
Exactly.
And it needs to return back a new function that was piped, and that is going to receive a single input value that it passes along to the first one. Now my strategy here is to be able to handle any number of functions. Essentially, I want to call the first function, and then whatever it returns,
And then whatever it returns.
and if there's another function, that becomes the input, and we save that output. And then just keep doing that until there's no more functions, and then I have my output. So I'm just going to set up a simple for loop, let fn of fn's,
Mm-hmm.
and I'm going to say b equals fn passing in b. So in other words, take the current input, whatever it is, pass it into the current function, and capture that output. And then iterate the loop again. If there's another function, do that again and again and again. And at the very end, return b. That should handle any number of functions. Implement the compose function and gather all of the functions.
So this is also something that I do this of redoes. Exactly.
An array called fn's, and I need to call fn's. I need to pass fn's to the pipe, but I need to reverse the order. So I'm going to say return pipe. I'm going to pass in fn's that make them spread. Yes. You can start with compose. It's just a little less clean because the for of loop, if you choose to use a loop, you still go to the reverse of the array rather than arrays. All right, let's test this.
Mm-hmm. Unless you say redoes right from this, and then once that is done, and then you want to return is that, and the same will be for this. If you say now that this will be in terms of compose, you say compose, you redoes right, so you go through the right element, okay, and then you apply all of that, and similar to the pipe here, you're gonna get this list of the functions, and then what you're gonna do is decompose, right? So return decompose in a reverse order, or not like that, because you need to pass the function here in this reverse order. Exactly. So if you run this and say ls cd composition, and then you say no.x.js, you see that now we create is that as expected. So function 1 is equal to 3 because first we pass is the value of 3. So we decrement that and then we increment that, and this is true. And the other is that f2 is say f1 is equal to f2. F1 is a compose, which is say, hey, I want you now is 3, decrement that, which is 2, and then increment that, which is 1. And the f2, which say, hey, I want you to now is decrement first, which is 2, and then increment that, which is 3, And this is true. And holy moly, we create now our God. Jesus, French toast. We create now our compose and pipe functions. Holy moly, bro. Call the specific callback function for the elements in the array in a descending order. From the most, or from the reverse, from the last element to the, in a descending order, from the last element to the minus one, or from the greatest to the minus one. Holy moly, bro. Holy F. So we create now our compose and pipe. So we take this list of elements, we take this collection of functions, right? And then we are returning is a function that is going to receive is the values, all right? We're assuming that for the sake of simplicity is only one, okay? And then you want to do is just to now starting the collection of this function execution from the most righteous element here, and then now you're going to pass this the accumulator as the value. That'll be now the input of the function of that, and then you're going to return that value. That will become is the returning output on the accumulator that will act now as the input of the new function, that once you move through the most righteous to the left elements, it will be now the input of that, and so on and so on and so forth and so on. Holy moly. And then it's going to compute all of that, because that's what Redux does, is to give in this collection of elements, it's going to apply this set of transformation and accumulate its value and then give you the outcome. This is mind-bending stuff, bro. This is mind-bending stuff. Holy F. This is truly mind-bending stuff, bro. God damn it. Holy moly, bro. And I figured it out, and I figured it out just by walking through that and apply all of those concepts that I already know that. Holy moly. We add a commit, because we need to add those changes. Right. We need to add those changes. We add that commit to the branch, and therefore now we're going to apply is this, all right, with our new state of the application, okay, which is the collection here, all right, compose and pipe solution using Redux. Holy moly. And you say git push origin to composition. All right, it's going to allow me to create now a PR, where this PR is say, hey, this is composition. An illustration. Oh my god. So an illustration here, an illustration of how to compose and pipe functions, a critical component or a critical idea in functional programming that takes exactly a critical idea in functional programming where a critical idea in functional programming where where the value proposition of compose and pipe is to see the data flow much more clearly, right? Compose and pipe allow us to look at the data flow, to look descriptively, or to look the data flow or allow us to glance the data flow in a descriptive way. Holy moly, bro. Jesus. Holy moly, bro. Oh my god. That'll be all for this video. Take care. Bye bye.